Well, here's an example following on from a regression equation. I'd already obtained the regression equation was y equals minus 4.71 plus 0.401x, and I've got to make predictions for 13 minutes from switching on and 60 minutes for switching on. So my first x value is 13. So all I need to do is take my regression equation and slot x equals 13 into that, and if I do that, then I have to do minus 0.471 plus 0.401 times the 13. There's that substituted in for x. Do this on your calculator and you get a value of 4.74 degrees. And then we've got to do the same thing for 60 minutes, so we just do the same thing with x equals 60. So I've got a 60 here for my x, and I got 23.6 degrees. So making predictions is just a matter of substituting your x values into the formula. But now I've got to comment on validity. Okay, and then now there is a difference between the x equals 13 and the x equals 60. And to see what that difference is, I need to look at the table of data. So here's the data from earlier in the question, and my two values of 13 and 60, I can see that 13 is towards the lower end, but it's within the original range of x values, whereas 60 is some way after the original range of x values. Now that makes a big difference. At this stage, I'm just going to say that for 13 degrees, it may well be the case that my prediction is fairly reliable. We've got more to say about that when we've looked at some residuals. But I can certainly say that 60 is not an appropriate value, because that would be extrapolation. That's the word you need to use when the value you're predicting is beyond one end or the other of the original range of data. So here I've made those two comments. I've started with x equals 60. That one is unreliable because it is extrapolation. That's all I need to say. Whereas the prediction for x equals 13, that's not extrapolation, so maybe that one's reliable. But as I said, there's more to say about that, and that's coming up in part G, where we have to calculate the residuals. So here's the table of data. So I've got the measured y's for each value, but I can compare the measured y's with the predicted y's. So if I were to, for example, find a prediction for one of these numbers, I would substitute it into this formula, okay, the regression equation, and get a value, and then the residual. So the equation for residuals is that the residual is the actual value minus the predicted value. So putting that into practice for this particular table of data, this is what I'm going to get. So it's the true value minus the predicted y. So for 20, 7.7 is the true value, but if I put 20 into the equation, so if I did minus 0.471 plus 0.401 times 20 in for my x, it turns out that I get 7.55. And when I do the subtraction, I get 0.15. So it's positive because the real value was greater than the predicted value. And I've done the same thing for 30. I put that into the formula and I got 11.56, okay, which 11.7, the observed value, is greater than that, so again I get a positive residual. And then for 40, when I put 40 into the regression equation, it turns out you actually get 15.57, which is greater than the 15.4, so now the true value, the observed value, is less than the predicted value, so I get a negative residual of 0.17. So that's how we calculate residuals. It asks us, does this change our view of the reliability of the predictions? Well, we've sort of left it that 13 might be okay, but now we need to decide whether the residuals, which kind of measure the error, are these errors acceptable or not? And the guideline is that if the residuals are within 15% of the true values, that's not too bad. So I need to look at the residuals, and I need to pick one that I think is pretty much the worst case in terms of percentage error. So the biggest residual, I don't really mind for this whether they're positive or negative. They're telling me how far there is, the size of the gap between the true value and the predicted value. Now, the very biggest residuals are things like 0.17, 0.15, 0.14, 0.15 again here. But this one's very nearly as big, and here that the actual value, the 3.4, is much smaller. So I think actually the worst case for percentage error is going to be this. So the error is 0.138. The true value is 3.4. So my worst percentage error that I can see is going to be an error of 0.138 compared with a true value of 3.4. So I need a percentage calculation. It's 0.138. The 100% value, the actual value, is 3.4, and I need to multiply that by 100 to get my percentage. So 0.138 divided by 3.4 times 100% is an error of 4.06%, 4.1% if you like. So this is less than 15%. Okay, so 15%, up to 15% is a sort of acceptable percentage error. This is much less than that. So therefore, the prediction for x equals 13 is likely to be reliable. Okay, but I'm not going to change my mind about the extrapolation one. 60 is well beyond the edge of the data, and the prediction for x equals 60 is still extrapolation. So I still regard that as unreliable. So residuals are interesting when you're looking at a non-extrapolated prediction, but nothing can rescue an extrapolated one.